All right, you guys, notes for chapter 13. I know chapter 13 is atmosphere and climate change, but last night my husband and my middle kiddo, we were walking in the subdivision and we saw the string of, I kid you not, 60 lights. And and first of all, I want to apologize for getting this video up so late. So right now, this is Friday, May 1st. So this was Thursday, April 30th. I can't remember what the name of it, but apparently it's these 60 satellites that go around in orbit around our planet, and it was probably one of the coolest things I've seen. So keep an eye out. And my husband saw two shooting stars. I saw one, and then my son stayed out a little bit later, and he saw another one himself. So I don't know if maybe we have a little bit less light pollution right now, but keep an eye out in stars and skies right now. But May 4th, we've got a meteor shower, 30 plus meteors per hour, so shooting stars per hour. May 7th, we've got the last supermoon of 2020. It's called the Milk Moon. May 12th, close approach of the Moon, Jupiter, and Saturn. And then May 27th, Comet Swan will be visible to the naked eye. So just some stuff I saw pop up and I thought it was kind of cool. I hope you guys forgive me for taking a few minutes to talk to you about it. All right, atmosphere. Yes, I apologize. There was no essential question. Come up with it yourself. You know, we've given you a lot of the essential questions. You guys can come up with some of them. I'm going to zoom in a little bit. All right, and we're going to go ahead and change our pen colors. You know how I like doing that, our 3 colors. And you guys have been so great about this. So, first of all, weather. Weather is the state of the atmosphere of a particular place and time. Okay? Climate, however, so what's the weather today? What's the climate of North Florida? That's your long-term prevailing weather conditions at a certain place based on records taken. Now, latitude is flat. Lat is flat. That's how I remember it. It's the most important factor in determining climate. Our planet, right? It has a 23.5 degree tilt. Please make sure you know that. 23.5 degree tilt. When I went for my master's degree, we actually had to answer a bunch of random questions, anything possible about science. And one of the questions I had was what causes the seasons? And that right there is your answer, 23.5 degree tilt. And that was something one of my middle school teachers had taught me, and luckily, for some reason, that number stuck. So you never know what kind of stuff stays in your brain. So latitude is your distance from the equator, right? So going either north or south. So 90 degrees north, that's your North Pole. 90 degrees south, that's your South Pole, okay? Your exact opposites. Equator is 0 degrees, North Pole's at 90 north, South Pole's 9 degrees south. There should be degree signs right there. I apologize for that. Degrees and degrees. Okay. It influences the amount of solar energy an area will receive because different amounts of solar energy falls on different parts of the Earth equals different climates. The seasons are caused by the tilt of the Earth on its axis as it revolves around the sun. So you've got the sun right here, right? And as the sun rotates around, so the sun right here is hitting the northern hemisphere, so this is summer. As this part comes all the way over here, right? Now this part of the northern hemisphere is furthest away from the sun, my hand being the sun. Well, that northern part is no longer getting the direct sunlight, so that's why you've got that part is going to be the winter. But then this part of the southern hemisphere is closest to the sun, so now you're in the southern hemisphere's summer. That's why we have opposite seasons between the northern and the southern hemispheres. Okay? You've got no seasons at the equator. Solar rays strike at 90 degree angle year round. We'll look at slides 1 and 2. Okay. Low latitudes, the sun's rays strike straight on. Oh, I'm going to change that color. Yep. Straight on. So you've got more solar energy at night and then a day, and that equals 12 hours each. you've got high temperatures. There's really no summers or winters, okay, because it's equal. It's always the same. At high latitude, the sun rays strike at an angle, universal sign for angle, or angle. So the energy is spread out. You have less solar energy. The amount of daylight is going to vary depending on the season, right? The temperatures are also going to vary, and obviously, whoopsie, you have seasons. Yay! We have seasons. So what does that mean? Well, let's look at our seasons, okay? December 21st, that is winter solstice. On December 21st, that is the shortest day of the year for us in the northern hemisphere. It would be the opposite for the southern hemisphere. It'll be the longest day for them. Then we go right down here. So we're getting closer for northern hemisphere. This would be March 21st. So that's the first technical day of springtime. Apologies. That's the vernal equinox. And then we hit June 21st. That's the summer equinox for the northern hemisphere, winter equinox for the southern hemisphere. And then you've got September 21st. And that's this autumnal equinox for the northern hemisphere. That's when fall starts. So December 21st, March 21st, June 21st, September 21st. It might deviate a little bit if we are in a leap year, but most of the time the 21st is it, okay? Every 3 months. December, March, June, September, all right? And the seasons change are due to what degree tilt? What degree? We talked about it. 23.5 degree tilt on the Earth's rotational axis. Going back to the notes. All right. Number 2, atmospheric circulation patterns. See? Okay. Cold air sinks because it's denser than warm air. We've talked about this a zillion times, right? In the summer in Florida, you don't want to be on the second floor of the 2-story house because that's where the hot air rises. Cold air sinks because it's denser. As cold air sinks, it compresses and it warms. Warm air rises, it expands and cools as it rises. That's going to cause a circulation. Warm air is going to hold more water vapor than cold. That's why we have more humidity down here. When warm air holds more water vapor than cold air, when warm air cools, the water vapor it has may condense into liquid to form rain, snow, or fog. Wind, movement of air within the atmosphere. You've got the global circulation patterns created by mass movements of air. Prevailing winds, these are winds that are going to blow predominantly in one direction throughout the year. So, I'm going to show you a way to remember the difference between trade winds and westerlies as soon as we look at the slide, okay? Trade winds are between the 30-degree north, south, and westerlies are between 30 and 60. So trade winds are between the equator and 30, and then between 30 and 60 are the westerlies, okay? So let's look at slide 3 again. Okay. So, hot air rises and holds water. Cool air falls, right? The trade winds are from the east, and they're found between 0 and 30 degrees. The westerlies come from the west. If you always think of where they come from, it's easier. Westerlies come from the west, then trade winds are going to have to come from the east. That's the opposite. And they're going to be between 30 and 60 degrees. Okay? So convection cell, right? Cold air falls, boom, it starts, gets here, it gets warms up, it's going to rise, and then it cools and it falls again. There's that convection current that's going to be created. Well, that's what's happening here. Except that as it warms, comes up, it starts to cool, it falls back down. It does the opposite and creates all these little cells, creating these trade winds and these westerlies, and then easterlies above the westerlies. Okay? That's what creates all these fairly consistent weather patterns that, for the most part, weathermen can use as guides of what the weather's going to do. However, there's always something that's going to act up, some change that occurs, because there's no, the one thing that's consistent in life is inconsistency. So when that happens, the weather acts up and we change accordingly. I'm changing color. I like that one, gold one. Okay. Oceanic. So if we have atmospheric, of course we're going to have oceanic. Oceanic circulation patterns. It affects climate because water holds a lot of heat, right? There's a whole lot more heat in the ocean than there is in the rest of the planet. Ocean currents are caused mostly by wind and the rotation of the Earth. El Nino, southern oscillation. This is going to be a short-term change in the location of warm and cold water masses in the Pacific Ocean. It's very, very common Pacific. You may not have heard about it, no problem. If you watch TV shows, El Nino is referring to Christ, actually, the Christ being born, Christmas time, because it occurs right around December. Winds strengthen and push warm water east. Rain will soon follow. Oopsie. I don't like it when it does that to me. Page 2. El Nino is the warm phase. After El Nino hits, usually the following year, you're going to have La Nina, which is the cooling phase. Pacific Decadal Oscillation, it's a long-term change, about 20 to 30 years in the location of water mass in the Pacific Ocean. That's going to cause these big, big, big changes. You'll notice okay, I'll hold off. Sorry. Then you've got geography or topography. The height above the sea level, temperatures fall 6 degrees every 1,000 meters or every 3,000 feet. Increasing elevation, mountains and mountain ranges influence the distribution of precipitation. It's called a rain shadow. We'll go to slide 5. There we go. So here's slide 4. Sorry, let me do 4 first. El Nino, that's the warm first phase. And La Nina, the cold phase, which will be second. So here you've got these warmer currents are going to come in. So remember the Pacific Ocean, that's where the kelp forests are. So all of a sudden, areas that are used to, because normally the ocean water in the Pacific Ocean, the northern part, goes like this. So it has all this cold water from Alaska coming down here along California. So all of a sudden, this whole warm water comes in. Those areas, those kelp forests are used to 50-degree water. Now all of a sudden, they've got water coming from the equator coming up. That's not okay. That's going to cause a huge uproar, right? So they get hit with this warm water, and they're like, whoa, whoa, whoa. They try to recuperate. And then right afterwards, La Nina comes in. We're sorry. Let's go ahead and freeze you real quick. We'll give you a second shock. Bring all this cold water right back. It's a shock to the organisms there, and it's a big hit. And never mind the change to the weather patterns. And sometimes it can affect it all the way up to a third of the country over, weather-wise. Okay? You have this link right here. Please take the time to look at that link. It really explains El Nino and La Nina so nicely. I wish I'd had that when I was in college, because let me tell you, I've had so many attempts to try and understand both those concepts. I watched that video and I went, oh my Lord, that was so much easier than anything anybody's ever shown me. So please, please, please take a look at it. And then like we mentioned, right, we've got that rain shadow right here, okay? You've got that warm rain shadow. Warm, dry air on the mountainside where the wind is flowing down, right? Warm, moist air, it comes up. All of it gets rained on, and the other side becomes this rain shadow. It's dry, desert-like conditions. Start looking at all the mountains set up in California. You've got this beautiful, lush vineyard, and then you've got the Sierra Nevada on the other side. It starts to make sense. Again, really cool video explaining this. Please watch these videos. You know I'm all about 5-minute or less videos, and it's really cool and interesting. Please, 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 please watch them. Okay. So, then we have solar activity. I have to change color. The increased solar radiation, more ozone, is going to cause a warming effect of the planet. Number 6, you have volcanic activity. Sulfur dioxide haze from eruption is going to reflect sunlight to cause global temperatures to decrease. Okay? Now, ozone shield. Remember we talked about the different layers of our atmosphere? So you've got the ozone layer, area in the stratosphere where the ozone, O3, not O2, right? O2 is oxygen, O3 is ozone, is highly concentrated. It absorbs most of the UV from the sun, like global sunscreen. And then you've got chlorofluorocarbons, CFCs, chlorofluorocarbons, class of human-made chemicals, human-made, we made these guys, that damage the ozone layer. It's non-poisonous, non-flammable, coolants, fizz and foams, propellants and sprays. That's where you're going to find all these CFCs, okay? Most of our hairspray, for example, or room deodorizers, you'll see it'll have CFC, like this, boom, CFC, a circle and a line through it, telling you it does not have CFCs. The problem with them is that they're very stable at our surface, but they're very unstable up in the stratosphere. So as it goes up in atmosphere, it becomes unstable. The UV breaks down CFCs and O3 into O2 and chlorine. Go back to slides. All right, so how CFCs deplete the ozone. This is showing you. So developed countries were producing a lot of it, and then in the 1990s, we dropped, and we have not gone back up. This is developing countries. We've actually been below developing countries, so we have really done a great job in the production of CFCs. We've stopped producing them. The problem we have is that it takes a long time for the CFCs to actually completely disappear from our atmosphere. Okay, so we stopped doing damage in 1993, I would say, and that's great, but it's going to take decades for it to be out of the air. Well, here's the great news we've just heard. I don't want to jump ahead. No, they're jumping ahead. All right. Changing color, purple. So, from these chlorofluorocarbons, we ended up with a hole in the ozone. Okay, thinning of the stratosphere ozone that occurs over the holes in the springtime. So let me go back again. Believe it or not, the biggest hole in the ozone. So imagine all of a sudden taking a giant towel and wiping the sunscreen away from our planet. That's what we've done with the release of CFCs. We've wiped away our sunscreen. And the biggest hole we have, of all places, is over Antarctica. And you'd be like, wait a second, there's the fewest people living in the entire world is in Antarctica, and you're absolutely right. So why in the world is the biggest hole in Antarctica? Because of those dang on weather patterns, because of those air circulations. All of the pollutants all ended up trapped right there. The hole in the ozone was the size of Texas. Everything's always the size of Texas. Truly, all jokes aside, the darker blue it is, the thinner the ozone protective layer is. So this was in 2007. Like we said, we'd stopped using the chlorofluorocarbons in 1993. We stopped. I mean, that was it. We were below developing countries, in developed countries, production. But it took that long for it to stop. And guess what? They just released, not 2 days ago, the hole's closed. Now that is phenomenal news. That means that we no longer have bad UV rays coming in, right? Does that mean that you can go outside without sunscreen? No. You still need to use your sunscreen. You still need to be safe about the sun. There's still UV rays that come through the ozone, okay? Be smart. But it's great because for a while we had so many UV rays that was coming in that there was an increase in cataracts, not only in humans but in animals too. Seals and sea lions were actually showing signs of cataracts in the wild because of this. because the UV rays hit the water, reflect back onto them, and it's actually worse. If you've ever been outside on the water for a little too long without sunglasses, you know what I'm talking about. Now imagine these poor animals who are out there 24/7. So the fact that the hole is closing up is phenomenal news, right? Let me fill in those little gaps right there. So amphibians, so some of the problems we had: increased evidence of skin cancer. Oh yeah, really cool website, shows you how the hole has changed over time. Amphibians, reduced egg survival, genetic mutations, that is putting it mildly. Among survivors, increased susceptibility to other stresses. Marine life, death of phytoplankton and surface water, that's a big problem since these guys produce a lot of oxygen for us. Then disruption of food chains, since they're the base of most food chains in the oceans. Reduction number of photosynthesizers, no joke. Land plants, interference with photosynthesis, that's a little bit of a problem. Because again, they produce oxygen. And not only are they producing oxygen, but they're sucking up our carbon dioxide. So let's talk about that for a second. That means our carbon dioxide levels were going way up. So we're going to talk about the hole in the ozone again in a minute, okay? When we come back, we've only got one more slide to look at. So, effects of ozone thinning. We're all exposed to more UV rays, which damages skin. Humans, skin cancer, cataracts. Cataracts is, you've probably seen this in older people. There's that haze that covers the eye, and they have a hard time actually seeing anymore. Got a weak immune system. Animals have genetic mutations. Death of phytoplankton and disruption of food chain, reduction of amphibians because their eggs are hurt. Plants, you've got interference with photosynthesis. And obviously reduced crop yields, which is our food. Protecting the ozone layer, which limit the production and use of CFCs is what started protecting our ozone. Use CFC replacement, success in getting the global community to cooperate. I mean, it was phenomenal, truly phenomenal, guys. The hole is going to be there for a while, though. I mean, but look at that, 2020, we got it done. CFCs can be active for 60 to 120 years. So molecules released years ago will be damaging the ozone for years to come. So the hole is closing, but we still have some areas that are thinner, hence why you still need to use sunscreen when you're out and about. All right. Global warming. Okay, the greenhouse effect. Let's talk about this. There is a huge misunderstanding about this whole process right here. So let's talk about it. Okay? So if you've ever been in a greenhouse, you probably walked in, it's probably very hot, muggy, right? Because basically the whole point of a greenhouse is to be able to grow crops or plants year-round regardless of the cold or weather. So it's trapping heat, right? Because that's what the plastic is doing. The hot air is rising, the moisture is being trapped in, so you don't have to water them as much. You still have to water them, of course, but not as much. So the moisture is being trapped in, the heat's being trapped in regardless of the temperature outside. Because I mean, we've all been outside and it may be cooler, 30 or 40 degrees, but you've got sunlight. Well, look at that. You're trapping this, you're keeping the heat inside, the moisture inside. The dry air coming in on the outside is not drying out the plants. So it's a good setup. And that's great unless you're a planet that's slowly getting hotter and hotter and hotter. And that's what's happening. Remember how I talked about the ozone hole, coming back to it? All right. Greenhouses typically are going to have a window that you can open. So if it gets too hot, you just open, let the hot air escape, and then when you've got let out enough hot air, you close it, and then we're great. So with the ozone hole being there over Antarctica, it actually allowed some of our heat that our planet was producing escape. By closing the hole, it's great because now our UV rays are being completely blocked a lot more, sorry. But the bad part is now we're trapping all the heat again. And we've not gone down in our carbon emissions. So we're still heating up the planet. And now the window that we had for hot air to escape is closed, which is a good thing. But now our planet's heating up even faster, possibly. So that's the problem we have. So greenhouse effect, where the Earth's atmosphere acts like a glass in a greenhouse. Greenhouse gases, these are gases that absorb and radiate heat. I'll go back to this in a minute. How it happens, you've got solar radiation that warms the Earth's surface. Thank goodness. That's why we're the third rock from the sun, right? The third planet. Any closer, too hot. Any further, too cold. We need to be close enough to get some heat. It's absorbed and radiate into the atmosphere as heat. Greenhouse gases absorb the heat and radiate it back towards the Earth's surface, because you don't want to lose all of that heat. I'm switching. Agreed. A greenhouse lets its solar radiation to heat the air, and the glass prevents the warm air from escaping. Average yearly carbon dioxide concentration in the atmosphere has been increasing. Increases by a few parts per million, ppm, parts per million, each year. Now, I was shocked when I found this out. They've actually been measuring our carbon dioxide emissions since 1958 in Hawaii at the top of volcano Mauna Loa, because that's how long they've been worried about it. This guy named Keeling. Burning of fossil fuels is going to increase our carbon dioxide emissions. Vehicles, industry, all add to carbon dioxide. Scientists have confirmed that because greenhouse gases trap heat near the Earth's surface, more greenhouse gases in the atmosphere will result in an increase in global temperature. Comparison of carbon dioxide in the atmosphere and average global temperature supports this view. Let's talk about global warming. An increase in global temperature due to the increase in greenhouse gases in the atmosphere. Increases in greenhouse gases are due to human activity. Well, the good news is, if it's due to our activity, then if we alter our activity and we do some new cooler activities, then we can help bring it all down, right? Burning fossil fuels, industrialization, deforestation, etc. These are all increasing the temperature, the temperature of the planet. Consequences of a warmer Earth. You've got melting ice, which is going to result in rising sea levels. Coastal regions will be affected. Flooding, erosion is going to occur. Global weather patterns will be affected. Surface ocean currents could change, thus affect weather patterns. Human health problems. Heat-related deaths, increased surface ozone, so increased respiratory problems, increased insect-borne diseases, things that we've seen. Agriculture, you could have an increase in droughts, decreased crop yields, which means not enough food for everybody. Plants and animals, you can have a change in range, i.e. changing where they live, of species and communities, land and aquatic, both. Findings from the Intergovernmental Panel on Climate Change. IPC, temperature rising, human activities are putting more greenhouse gases in the atmosphere, sea levels are rising, etc. So, what can we do to reduce the risk? You have the Kyoto Protocol, which requires developing countries to decrease emissions of carbon dioxide and other greenhouse gases. You've got reforestation projects, so planting more trees. You've got the Paris Agreement. Developed countries commit to keeping warming below 2 degrees. We're currently at only about 1 degree increase in the planet's temperature, guys. So if we're seeing the kind of issues that we're seeing, and the planet's only going up 1 degree, the fear is what is going to happen when the planet's gone up 2 degrees. Okay? And bottom line, we don't want to see it. We don't want to find out. We're going to do stuff to fix it. Okay? You've got another good little video right here done by NASA to see it. And then you've got some major greenhouse gases. Carbon dioxide. What we breathe out is technically a greenhouse gas. Methane, What we toot is a greenhouse gas, nitrous oxide. Water vapor, water itself, because it traps heat, is technically a greenhouse gas. So am I saying get rid of water? No, obviously not, because we need it to survive. And then let me go back to this last slide. All right, so we've got the greenhouse effect, right? So it's normal for some of the sunlight to come in, hit the planet, warm it up, and go back out. That's normal. This situation right here is normal. What's happening is the more greenhouse gases we have, it comes down, hits the planet, comes back up. It hits those greenhouse gases right here, and it goes back down and warms it back up and goes back up and hits it back down and heats the greenhouse gases up again, comes back down. It keeps coming back down and warming the planet. That's what's causing the planet to warm up. And it's all because we keep releasing these greenhouse gases that creates like this giant blanket. I think that's the best way to look at it. Think like a blanket. All those greenhouse gases are molecules that are acting like a blanket, warming our planet more and more and more and more. Okay, so you have methane, you have nitrous oxide, N2O, you have carbon dioxide, CO2, ozone, O3, you have chlorofluorocarbons, CFCs, carbon monoxide, CO, and sulfur dioxide. And then you've got a bunch of different breakdowns based on worldwide emissions of carbon dioxide in 1995 and then in 2035. Okay, guys, so I hope you understand a little bit better about atmosphere and climate change and all that. Okay, so based on global warming, it's causing a worldwide climate change. Okay, all right, if you got any questions, make sure you shoot them to me.